we'll
The beginning of this one might be a little dead until you get into content, but it's still good.
But it's really hard to sort through video if it's all 4 hours straight.
Yep. I don't want to spend as much time as going through all these slides would take. I'll try to just blast through this, okay? So I mentioned that the Beaglebone Blue is a robotics cape plus a Beaglebone Black wireless, right? So, and that project came out of the University of California, San Diego. So this is what the Beaglebone Blue looks like. That's the chunk that is essentially the Beaglebone Black wireless. Struck down into a SIP, kind of helps it make it easier for you to customize too. This is the big ad. We're going to go into the schematic on this one, which is this.
Pause just for another.
Sure.
So you have SD cards in your kit. So
Do those need to have what's on them already, or can they be replaced?
we're gonna overwrite these. So this
Okay.
is kit 5. It should have SD card 5 and 15. Okay. So this is MXET card 5. You can write on top of it. Okay. So team 2 is me and Austin, Sudeep and Cyrus. I don't know what team you're on, but you're not team 2.
Yeah. Oh, it's team 3. Team 3.
Okay, go ahead and fix it. And then your SD cards are, does everyone have one SD card per person? No. Okay, do you need one?
You need a pen? Ultimately, we're gonna turn these we're gonna use these SD cards to program the boards, and then we're gonna from the board program back the. Did you just write back on team 2 instead of team 3?
Yeah, you guys, your number, your grad students, I think you can figure this out. So Jonas, you're also on team 3? Okay, so the 3 of them. And then your Beagleboard, I believe one of them is already on your robot. If you don't need to remove it, you can put your SD card in there without removing it. The other one, the other Beagle is in the box. So we will. Are we putting the first image on the edgemint?
Yes. We're gonna program the edgemint first.
So you don't need them yet, but we want to do as many duplicates of this. Even though you're all sharing a robot, we want to still etch double. Everybody etch as much as they can so that we can catch any problems or questions.
You mean write the SD by etch? You mean write the SD cards? No, what do you mean by etch?
Yeah.
Yes.
Okay.
He's referring to that, sure.
Right, because it's just such a fundamental thing, right? That this is how you reproduce the software configuration that other people have. Is so downloading an image file, putting it on an SD card. We're going to use what's called a flasher image. So there are 2 different types of images, and we'll show you a little bit about that. I don't have great slides for it. Unfortunately, it's going to be a little bit of show, but I'll try to write in some things in the notes. But ultimately, you're going to learn how to create this image for yourself.
So Jonas, are you still missing an SD card?
Yeah, I got it.
Okay. So everyone has their own that they can write.
Okay. So the LiPo battery support, which I know we've got a section, there's some stuff we have to get into, but there's an IMU on board, so it has a built-in gyro, compass, accelerometer on there, as well as temperature and pressure sensing. So you get altimeter. There's motor drive. So there's servo outputs, which send varying pulse widths. So you get a pulse for setting the orientation of a servo, as well as a 6-volt output powered by the battery. All right, so the power is directly from the battery through a 6-volt regulator in order to drive the servos. And then the DC motors, that's directly battery voltage. but gone through a PWM H-bridge. Are those terms all come for PWM, H-bridge, 6-volt regulator, all that stuff is all good terms, okay?
You've got to ask if you don't know what the term means. Everyone knows what an H-bridge is?
No, I don't know H-bridge, but.
Okay, great. So I've got a slide to answer your question. It's just I don't find a slide with an H bridge.
Is it okay if his, that we just use one, read it as SD card?
Data motors. Yeah, I should speak with slides open all the time anyway, right? So. So a DC motor, right? For most part, if you'd be working with DC motors, right, that you just apply a voltage to and it then begins to just free spin. So an H bridge allows you to reverse the direction of that. So you've got a voltage source, and essentially what amounts to 4 switches. So if S1 and S4 is closed, we're essentially spinning it in one direction. If we open up S1 and S4 and close S2 and S3, now the voltage is running through the opposite direction on the motor. So an H bridge allows you to flip that over. And then the PWM is what allows you to essentially set the strength, right? So it's these pulses, you're not actually producing a varying voltage. The voltage is just on or off. But by how long that it's on, you're varying the drive strength. So the combination of a PWM and an H bridge allows us to drive a DC motor in different directions and at different speeds. One interesting thing about these H bridges is that you can also set you can do braking. So if you leave the circuit connected but drive 0 volts, essentially the motor acts, that motor turns into a generator, right? So it's going to, as you're turning, it's going to try to generate a voltage. If we're essentially sinking that in our voltage generator, then it's going to try to hold it where it's at, right? It's going to act as resistance to that motor turning. If instead we become a low impedance path and we don't hold that voltage, right, we become a low impedance path instead, the motor's going to free spin. Good.
So when you're performing braking on the H bridge, it's the same as tying the ground to the positive on the motor leads.
Okay, so it's
Is that? I think then you have a situation where it wants to drive a voltage differential. So the black wire increases in voltage, but it can't because it's tied back to the.
right. It can't create the voltage differential. Right. So I guess it's a low impedance path for braking. Is that right?
Low impedance from terminal to terminal.
For terminal and terminal braking. One of those two. But yeah, if you prevent it from making the voltage differential, then it wants to stop.
We can try it later with when we play with the motor that's not connected to that.
So that we'll be able to. There's just a command line function that we're going to run on the boards to do braking as well. I don't need to go back into slides. So we talked. Trying to stay on a thread here.
Yeah. So you can do it right now on your robot actually. Bring the motor, and then tie your black and red together.
And you feel it's harder to turn.
If you Google it, go to the Wikipedia page, there's actually a truth table that shows you coasting versus braking, the different combinations from the same image you gave us, the 1, 2, 3, 4. It'll show you
Which configuration is braking?
which coasting, short circuit, etc.
Yeah. Because if you open up all the switches, you're essentially going to coast, right?
I think so, yeah.
And then if you close them, but fix the voltage at 0, then it's going to break. That's what we're doing. We were talking about the board. I won't spend too much more time on this. So you have DC motors, servo motor outputs, encoder inputs. So this is kind of some nice little magic. There's little AB pulses. I don't know if I have a diagram in this slide deck with it or not. But if anybody who knows the term gray code?
Gray code?
Gray code. Don't know the term gray code. It's kind of handy to know. So I think if we draw lines at these various sample points, we'll just draw 5 of them for examples. And if we read the values, this is 0, 0. This is we'll say this is the LSB and the MSB. Most significant bit, least significant bit?
Yes, sir.
Okay. So 1, 0, 1, 1, 0, 1. And then back to 0, 0. That's way too small, but hopefully you can kind of guess what the numbers are from that. Can I get on the camera?
Yeah. Now we can see everything.
The thing what those encoders do is as it goes through those pulses, as a motor turns, there's essentially this optical wheel, or it could be a magnetic wheel or anything else that essentially generates this pulse pattern as it turns, so you can actually know which direction it's turning, right? So as you turn the motor forwards or backwards, then it can say whether or not it's moved forward steps or backward steps, right? There's only a point in time where one of these changes at any one given time. So if I know depending on which one changes, I know which direction I'm turning. So the encoders are hardware that actually measures the amount of pulses generated. So I can know exactly where the motor is, so it just gives me a number, or I should say relative.
So your encoder, you read it and it gives you an integer number?
It's exactly right. So you just read,
How many?
so the peripheral, so the hardware just does the counting for you. So the peripheral, you just read it and it gives you an integer number.
And
if
it-
that number
it
is
basically-
increased, it's gone forward. If it's decreased, it's gone backwards.
And it reads in pretty much real time.
Absolutely.
You
Yeah.
probably couldn't find any device that spins too fast for it to count.
So it depends on, so the way you kind of, it'd be really, really hard to find a device that spins too fast that the encoder can't measure the pulses. That would be really fast.
In our world,
And in this
in our
world, it's
world,
never, you'd have to get into more high-powered, like really fast free spinning. But you do need to read it faster than it can overflow.
and how many bits is it?
It's a lot. I think it might be only 16-bit or something, but it's enough
So-
that
You can't figure out if
it's
it's,
never even come up as a problem.
you
so.
can't figure out how many bits you need until you also
Might
know
be
how many bits are in
32.
the revolution.
Right.
I wonder if it's printed on one of these motors. Actually, each one of you has one of these in it.
And I've got the wire on one, so we can actually read it back on that particular one. But there's encoders on the EduMap robot, so we're gonna read them off of that.
Here's my instrument.
Yeah, there should be one for each of the different scuttles. There's also a matching EduMap that we can use. So we'll read those. There's also a whole bunch of fixed function serial, things like SPI, I2C. Everybody, who knows what SPI is? Okay.
I can't characterize it though. Do we need to know? Do we need to be able to characterize it?
No.
It's a communication protocol.
It's a digital serial communication protocol. The big interesting thing is it's unlike a UART, everything's clock synchronous. So the UART, essentially you have to know the baud, you have to communicate the baud rate, which is the rate at which the bits flip. And then the way they're implemented is you oversample and you kind of look for like in the middle of where the bit would be based on what the data rate should be approximately. It's never perfect, so you have to resynchronize. But in an SPI, there's actually a clock. So you're sending the clock along with the data, and you're sampling the data on the clocks. And then I2C is a funky one that's 2-wire, where essentially the clock is embedded yeah, it's a little harder to explain. And there's CAN bus. So we have a CAN bus on here. If you use CAN bus, you do need to add a termination somewhere in the network. If you just put this in the middle of a network, you're fine. Right? That's the way it's currently configured. I believe that there's a pad to add a resistor if you want to solder down to the board.